little bit about myself. My name is Russ Cam. I'm originally from here, but I now live in Sydney. I'm just over here on holidays, and thought I'd sign up and succumb to a talk because I don't think anyone's been down this area. So, I thought I'd come and talk to you about Elasticsearch with .NET. So the agenda for tonight really is to give you an introduction to the Elastic Stack, get up and running with the .NET clients. How do you connect? How do you use it? What's the kind of idioms and conventions that are in the client? Then have a little look at indexing and mapping, search and analysis, which is kind of really the takeaway bit, I would say, of this particular talk. This talk is kind of geared more around search use cases than other particular use cases of Elasticsearch. And then finally, having a little look at aggregations there, so being able to group and summarize data. So who's actually using Elasticsearch here so far? Okay, who's played with it? Okay, a few people have played with it. Who's using it in anger? Who's using it in anger with the .NET client? Okay, I will avoid those guys. So yeah, a little bit of the history of Elasticsearch. So for a long time, Elasticsearch has been used with Kibana, which is like the visualization, the web, basically the web application. You can build dashboards based on the data in Elasticsearch. And then it's also been used with Logstash as well. The Logstash name is a little bit of a misnomer, but it's essentially a way of ingesting data into Elasticsearch. And those three things together have been known for a long time as the ELK stack. So about 2 years ago, 2.5 years ago, we actually added another product to the stack as well called Beats. And I'll go into what those are in a second. And then we were kind of thinking, well, how does Beats fit into ELK? Is it Kleb? Is it Belk? Is it ELKB? So we couldn't really sort of come up with a good name for it. So it's actually the Elastic Stack. So at the top there we have Kibana, which is basically your window into the data in Elasticsearch, allows you to build visualizations, dashboards, run ad hoc queries, you have other plugins in there for doing machine learning. And then at the heart of the stack is Elasticsearch, which is the search analytics engine. That's where you store your data. That's where you query all your data. Then on the ingestion side, we have Logstash, which is I best describe it as an ETL pipelining tool. So you'll run it centrally somewhere. You're able to set a bunch of different inputs, so like file inputs, inputs from RabbitMQ, inputs from Kafka. All of the well-used ones have inputs for them. Then you can define a bunch of filters that basically say how you modify that data. So it could be things like enriching data. If you're ingesting IP addresses, it could be getting the geo data for those IP addresses. And then finally, there's outputs. And one of those you can send to Elasticsearch. You can send it back to FAR. You can send it to SQL Server, numerous different places. Where Beats fits into this, so Logstash you would kind of run centrally. Beats are very much designed to do one thing and do it well. So there's a family of Beats, and basically those sit on the edge servers. They sit on the edge nodes, and they do one particular thing. It could, for example, be monitoring a directory and tailing the files that come into there, and then just sending those either to Logstash or sending them to Elasticsearch. So there's ones for FileBeat, MetricBeat for getting Linux metrics, like Windows event logs. There's a whole family of them. On the commercial side, so these are all open source. You can take those, you can run them. They're all under Apache 2. You can do whatever you like with them. That's absolutely fine. On the commercial side, and basically as a company, how we kind of make some money, is that we have these XPack offerings. Now, basically all they do is they extend the open source version. There's no freemium premium model here. These extend the open source offering. So they provide additional things such as security, OAuth authentication, LDAP authentication, user access control, role-based security, document-level security, field-level security, alerting, so being able to alert when data's coming in, when certain thresholds are maybe hit, send a message to Slack, send a message to HipChat, send an email, put it into another index in Elasticsearch, send it to a log file, that kind of stuff. Monitoring, being able to monitor the entire stack. So metrics coming out of Kibana, metrics coming out of Elasticsearch. So what does the JVM heap look like? What does the CPO look like on there? What's the search rate like? What's the indexing rate like? And getting those kind of metrics. Then a couple of newer ones here as well. Graph, being able to understand and infer relationships between documents in Elasticsearch. It's really, really cool. That's one of my favorites. If I've got time, I can probably give a demo of it. If not, grab me afterwards and we can go through that. And then finally, machine learning. So this element here isn't the big wide world of machine learning. This is very focused one specific use case for machine learning right now, which is unsupervised machine learning for anomaly detection, essentially. So a lot of people use Elasticsearch for time series data, and they want to understand anomalies within that data. That's where machine learning comes in. All of that stuff we offer on a software as a service on Elastic Cloud. So that runs on AWS, it runs on GCP. It doesn't run on Azure yet, unfortunately, but that, no doubt that will be coming. And then the second thing for Elastic Cloud is we actually offer Elastic Cloud Enterprise, which is the software that we use to run Elastic Cloud on AWS, except you can take that and run it on your own private servers. So you can spin up clusters using the same orchestration that we use for Elastic Cloud and use that internally. And that's, I'm not a massive fan of the name Elastic Cloud Enterprise, but it's kind of geared more towards the big corporations that are spinning up, you know, hundreds of clusters, which does happen. So what is Elasticsearch? So it's probably about half of you had already used it before, which is pretty cool. But essentially Elasticsearch is a distributed search analytics engine. That's pretty much in a nutshell, but what does that actually mean? So there's a few things to it, and we can kind of break them down into these three areas. So it's distributed and scalable, it's resilient, so there are mechanisms in there to ensure that the cluster remains operable when certain scenarios happen. It's highly available, so in the event that one of those nodes within the cluster actually goes down, you still have all of your data, it still operates in some capacity, and you haven't lost anything. Your ability to do multi-tenancy, so in Elasticsearch, you index documents into Elasticsearch, they go into an index, you can have multiple indices, you can search across multiple indices, you can search across multiple types, although types are going to be going away in the next version, so I won't say much about those. But you have the ability to multi-tenant there, and particularly with security as well, you can also ensure that people only have access to the data that they should. And it's able to deal with structured and unstructured data. So some people prefer to use it in the fashion of a unified logging format, so unifying what metrics look like, what log files look like, say from Apache, and unifying those into a common format and then indexing those into Elasticsearch. But you don't necessarily have to do that. If you're indexing data into indices in Elasticsearch, you can still search across those, across common fields, across different fields targeted at specific indices. It's very developer friendly. So this is how I originally got interested in Elasticsearch. Was I think it was around 2012. I started playing with it just for a bit of fun, bit of research, and just thought it was really cool and really interesting, and was amazed by the speed of it, and just kind of went from there. So one of the things that makes it very easy to get started with is people often refer to it as schemaless. I think that's not quite correct. I prefer to refer to it as an inferred or implied schema. So the first document that you index into Elasticsearch, if you haven't explicitly told Elasticsearch about the mappings for those documents, about the schema for them, it will infer the schema from that first document it sees, which is useful, particularly if you're ingesting new data. That can be a really useful feature. For search use cases, not so much, and we'll see why a little bit later. It's a JSON REST API. Essentially, I think there's now 160 odd APIs, I believe. So everything is over HTTP, JSON based. So JSON documents, indexing those, JSON back. And there's client libraries for pretty much every single language you can think of. So yay, .NET as well. There's actually 2 for .NET. But yeah, all of the well-known languages that you know. And it's open source, as I mentioned before. So you can take this, download it, start playing with it. be impressed like I was, and yeah, put it to some good use cases. The other awesome thing about it is not only is it able to scale, so we have customers running very, very large clusters. I was on a call with a customer recently, and they had a 400 node cluster. And yeah, I've heard of bigger ones out there in the field, but it's still very much near real time for search across all of that data, which, and when I say near real time, I'm talking usually under a second, like on a 400 node cluster, under a second result, you get results back, which is pretty impressive. Able to do full text search, so feeding back into the unstructured search side of things, so able to perform searches across unstructured blobs of text, essentially. Can also do aggregations, so you can combine the two. It's very useful for e-commerce sites, for example, where you need to perform a search and show results, but also show some facets on the side there. So for other like categories, say, of data that's coming back. And is able to do geospatial data as well. So you can combine geospatial with full text, with structured search, and combine all of those together for a very comprehensive search strategy. And obviously it's multilingual here as well. So able to index various different languages, and there are some other interesting things you can do around indexing different languages and using it to classify new languages as well. So given this document, I have no idea what language it's written in, being able to index it and using one of another feature in Elasticsearch, which I won't talk about tonight, but using percolation, you can get it to identify what language that document is, and then maybe tag it when you send it in. So that's kind of what it is. A very, very brief overview of Elasticsearch. So you run it in a cluster, and a cluster consists of a bunch of Elasticsearch nodes. So here, in my example here, we have a 3-node cluster. And when we index into that cluster, we're going to be creating an index. And for this particular index, I've said I would like you to create 3 shards for this, for this particular index. So all of the documents are going to be split across these 3 shards. Elasticsearch will assign a shard to each of the individual nodes here. So the P here is for primary shard. And I can also then set in the settings to say I also want a replica shard. So for each primary shard here, we can also have a replica shard. So as documents are coming into Elasticsearch and I'm saying go into this index, they're going to go into one of these primary shards. Elasticsearch is going to replicate that document over to the corresponding replica. Elasticsearch also balances where those replicas go in comparison to the primary shards. So it will never assign a replica shard onto a node that has the same primary shard, for obvious reasons, which will be explained now. So if we were to lose node 2, what we would end up finding is that this one replica shard here will end up being promoted to a primary shard, and the cluster still remains operable because we still have a complete collection of shards there. And then if that other node was then to come back afterwards, Elasticsearch will automatically assign shards onto it, and you would have your redundancy back again there as well. So that's kind of the way it operates. It's a primary backup replication model, which is very well known in distributed systems. So why Elasticsearch and why not SQL? So let's sort of take a little journey here and see if we can sort of understand why Elasticsearch is a good fit and SQL is great for certain stuff, but maybe not for search and analytics use cases. So we want to search in SQL, and we're looking for meetups happening in Bristol tonight about Elasticsearch in .NET. So how would we typically go and look for those, or how would we look for things around how to use Elasticsearch with .NET? So we might sort of form a SQL query like this, and we're like, yes, we get the one result back we're looking for, but we may have missed loads and loads of documents that are related to .NET, related to Elasticsearch, and related to other things to do with the Elastic Stack. One particular problem that we see here is that our particular database here is case sensitive as well. So we're like, okay, we can fix that by just lowering the title and then comparing against the lowercase. The other problem we have here now is that this is only ever going to match questions here that correspond to how do I use Elasticsearch with .NET exactly. So we've heard of this other thing in SQL, is like queries. So we suddenly change it to like query, and we're now looking for things that contain Elasticsearch with .NET. We're thinking, okay, we're doing pretty well here. We're getting back more results than we thought we would. But the other problem here we see now is that we're only looking for things that contain exactly Elasticsearch with .NET. So we're thinking, yeah, you haven't got me yet. I can still sort this out. So we split it up and we say where lower equals like Elasticsearch and lower is like .NET. And now, we're getting back more and more, and we're feeling kind of happy with it. And the boss comes to us and says, well, actually, I'm only really interested in the things in the last 3 months. Thinking, okay, well, that's easily solvable, where creation date was between, 1st of July and 1st of October. So we'll only want things in the last 3 months. Well, actually, no, we don't only want things in the last 3 months. We want things over all time, but if it's happened in the last 3 months, I want it to be more relevant than the next thing. So we're kind of scratching our heads a little bit, and we're thinking, well, how the hell are we going to solve that? We sort of come up with this concept of ordering by and preferring more recent, but we sort of start writing the user-defined function for that. We get sort of halfway through, and the boss comes up to us again and says, I'd like things more recent, but I would also like those questions that have a higher score to also be more relevant as well. So we sort of combine that with our order by idea, and we're really sort of scratching our heads here. And, in the end, we just eventually, we realized that, SQL is really not the tool for this, for performing this job. It will get you some of the way there. As soon as you need to do anything more complex, SQL is not the tool. Databases are good for database problems. Elasticsearch is good for search and analytics problems. And we'll see why that is the case shortly. So that's kind of an overview of Elasticsearch. Any questions? I should have said, feel free to just, raise your hand, shout out, whatever, that's fine. I try not to go down the implied knowledge route. So if anything I'm saying doesn't make sense, then just shout, and I'll try and reword it in a way that does. So yeah, Elasticsearch with .NET, we have 2 clients. So we have Elasticsearch.NET is the low-level client. It's dependency-free, has no dependencies on other NuGet packages, which makes a lot of people happy. It has all of the Elasticsearch APIs are mapped in the .NET client. And you deal with something called post data. Post data, some people love it, some people hate it. It's a general type that is able to handle a bunch of different primitives for you being able to interact with Elasticsearch. So for example, you can use strings, JSON strings, you can use anonymous types, you can use byte arrays, you can use streams with post data. So the intention with the low-level client is to basically not get in your way, just to give you the bare bones API implementation for you to work with. Then we have Nest. And Nest is the high-level client, and it represents all of the requests and responses to Elasticsearch as strong types. So easy discoverability there, hopefully, if there's documentation there for it. It has a dependency on JSON.NET. So whereas Elasticsearch.NET has its own small internal JSON serializer, this one requires JSON.NET, which is both good and bad. It's good because it's familiar to a lot of people. It's bad because obviously sometimes it can clash with other people's dependencies if they're not on the same versions. And it has a bunch of advanced features as well. So it has the concept of covariant search results. So if you're searching across multiple indices and you have a JSON representation that maps to a particular POCO, a particular C# POCO you have, and you're searching across multiple indices that have those different POCOs in them, we can still return a collection of covariant results there. Obviously, you need some kind of relationship to them, some lowest common denominator. It may be object, like returning a list of object, or it may be, some interface, but the actual types in there will be deserialized to the types that you tell us to. So we can handle covariant search results. It does other things such as retries and connection failovers. So if you're running against a particular Elasticsearch cluster and you seed it with the 3 IP addresses for the nodes that are in your cluster, it will fail over to those nodes and round robin requests over those nodes for you. And it does other things such as sniffing the state of the cluster. So if you have a cluster that's, say, grown to 6 nodes now, it's able to sniff that, bring back the details of those 6 nodes, and then run against those 6 nodes then. So there's quite a fair bit of smarts in there that you don't need to write yourself. So before we get started with search queries, let's kind of jump out of here and jump into some examples instead. So this particular one is looking at the Stack Overflow data, which I would love to show you if it was on that screen. 1 second, let's just duplicate this. Hey, okay, is that big enough at the back? Can you read that? Yeah. Okay, so yeah, we're just dealing with the Stack Overflow data here. So if no one's looked at it before, you basically have the concept of a post type, which has some general fields, and then you have a question type and you have an answer type, which both derive from a post field. So a question has a certain fields such as title, body of the question, well, which is common to both questions and answers. An answer is related to a question as well, which is what the parent ID here represents. So these are the types that we're dealing with and we've mapped. So if we were to get started with the low-level client, what we can do here is just send in a search request here to the posts index. So we're targeting the post index and we're targeting the question type in there, because in this particular index we have both questions and answers. And we can send in this anonymous type here, and this anonymous type really just is the same representation for a query that you would have in JSON expressed as an anonymous type. And what we can do is we can run that, and we probably won't get anything back because I don't think I've started Elasticsearch yet, and I haven't, no. So let's just start that as well. So I have all of the Stack Overflow data since eternity, since the start of time, indexed here on my laptop. Hopefully it'll hold up. I think it's about 60 gig of data, 60 gig of questions and answers. So let's run this one again, see what comes back. Okay, so we got some results back, and we were just looking for questions that have in the body of the question, this should never happen. And what we can see here is a massive wall of JSON. That's obviously not very readable for us. So yeah, that's brilliant, Russ. So what we specified here is this generic type here is the type that we expect to get back from Elasticsearch. So on the response here, we have some usual details around status codes, whether there was an exception on the Elasticsearch side, but the body part here is essentially going to be that string that we've asked for. And then all I'm doing is just dumping it out to the result window there. So that was a big wall of text. That's not very useful. So if we just skip forward to the next one, and I'll show you a slightly more complicated example. So we're still using the low-level client here, except that rather than just dumping it out straight to the window, what we're going to do is set up an action here that's going to be called whenever a request is made and a response is returned. So when the response is returned, this particular action delegate inside of here is going to run. So if there's a request body here, we're just going to write that out. If there's a response there, we're also going to write that out. So this makes it a little bit easier to see exactly what's going on. If we run the same request as before, we can see now we have a bit more form to the results. It's a bit easier to understand what's going on. So this is the request that went through. So it was a post to the posts index to the question type there and hitting the underscore search API endpoint. And these were the results that came back. So it took 133 milliseconds. It was a 200. And we can start to see a bit, well, other than that massive wall of text there, we can start to see a bit more structure to what comes back. So we have here details around the shards that were hit in the cluster. And then inside of the hits object here, we have total number of documents that match that. So there's 616 documents. Let me bump that a bit. There's 616 documents that match this would never happen in the body. And the max score assigned to those is this. and these are the first 10 results inside of this hits. So each object inside of here is what's known as hits metadata, and in there you get the index that it came from, the type that it was, the ID of the document, the score given to it, and inside of this source here is the original verbatim JSON document that was sent to Elasticsearch. So when you send a document to Elasticsearch and index it, you can say whether it should keep around the original source document. So when it does index it, you have a few different options. You can say, yes, I want you to index it for search, in which case it will go into a particular data structure, which I'll talk about a bit later. You can say whether it should store the original JSON document so that you can get that original document back, or you can say do neither of those things, in which case it makes Elasticsearch completely useless. But you're probably going to do one of those things. Now, usually for search cases, it's useful to keep the source around as well. If you ever need to re-index your documents, if you don't have the source there, you're going from maybe some other source again. So you usually want to keep it around unless you have a very good reason not to. So that's a slightly more complicated example with the low-level client. Let's get going with the high-level client. So just jump back a second here. So the low-level client, we've passed it in some configuration settings here. So we said, I want you to pretty print the JSON coming in and coming out. Disable direct streaming, which is essentially, I don't want you to write straight to the request stream. I don't want you to deserialize straight from the response stream. I want you to buffer those two things so that they're made then available to my action delegate here so I can print them out. If you decide not to do that, you won't get any request or response bodies, but you'll still get the stats around what happened in the request. And we newed up the Elastic low-level client here. So skipping forward to Nest client. Here we're using a slightly different connection pool. So as I mentioned earlier, we can seed it here with 3 nodes to say these 3 nodes are running in our cluster. These are our connection settings. If no index is defined when I make a particular API call, then use this index as the default index name. If you see a user type, post type, question type, answer type, use these particular index names. So that means we don't need to define them on every single request and response, on every single request. And there are other options here for basic auth, global headers, additional query string parameters. This one down the bottom here determines how Nest is going to serialize POCO property names. So by default, Nest camel cases property names as it sends them to Elasticsearch. So JSON document, they'll all be camel cased property names there. But this particular option here on configuration settings, you can change that if you want to. And then we simply pass the settings to the client. So we can do a similar thing as we did before with the low-level client. We can set up an action delegate and catch it. And now we can make a request here with the high-level client. So the way the high-level client works is there are actually 2 different APIs here. There's a Fluent API for those that are happy with Lambda expressions and heavily nested Lambda expressions. And then there are those for using more of a kind of object builder, object initializer syntax, as we call it. So same query as before, but now with the high-level client. So we can see here we have member expressions here to get to the body of a question. And this is our query here, and we can dump that one out again. And whoa, what's happened here? So index name is null for the given type and no default index is set. So on our particular setup here, we haven't defined what index the client should go and look in for the question types. So that's easily fixed for our particular request here. We can just specify index, posts, and then run that one again. Or we could have set up a convention on our connection settings and have that work as well. So all I've done here is just dump out the, let's zoom in on those. So all I've done here is just dumped out the bodies of the questions here from Stack Overflow. So jumping on. Oh, yep, sorry, yep. So that was with the Lambda expressions. This is with the object initializer syntax. So we can build a search request, looking at question types, and use the match phrase query, which is what we were using before. And we can simply then pass this search request to the client, and this is going to give us exactly the same results as we saw before, but no pretty table because I'm not building a table there. So that's kind of how you get started with search, and I'll go through some of the capabilities in a little bit. But you kind of need to get data into Elasticsearch first, right, in order to be able to search it. So Elasticsearch has a whole set of CRUD APIs to be able to do that. So give you an example here. We have a question type, and we can just index that question type into Elasticsearch. And what you'll see come back here is, so just checking whether the index exists and deleting it if it does. So that was these two calls here. And then we're just putting this particular document into Elasticsearch, and we got a 201 response back, so 201 created, HTTP response, and it gives us some details around exactly what happened there. That's great for an individual document, but usually we're talking about thousands and millions of documents. So we actually have a bulk API as well, so we can send through a bunch of a collection of questions, collection of answers, all through in one request at a time. So here we're just doing something very similar to what we were doing before, except this time we're defining the index up front. So we're creating the index. We're saying inside of this index, I want you to map a couple of types. There's a reason for doing that here. In our particular case, you can see that we have a collection of posts here with 2 questions and an answer. This answer here is related to this question here. So we have a parent-child relationship there between the questions and the answers, but we just want to index those all into the same index anyway. So we need to give Elasticsearch a bit of information here. We need to say that our answer type has a parent, and the parent of an answer type is this question type here. The auto map here I will explain very, very shortly, but essentially we create our index using this default index name, which is just a string. And we're saying we want to map questions and we want to map answers. Then we provide a bunch of posts, which is our 2 questions and answer, and then we call the bulk API. So in our bulk API here, I'm having to specify index all over the place here because I don't want to overwrite that 60 gig questions and answers index by accident. So I'm being very explicit around the index I'm targeting here just to demonstrate to you. So in our bulk API call, we have a couple of extensions here for you to be able to say, given each item in that collection, how it should be mapped, how it should be indexed. So we're just looking inside of this Lambda expression here, and we're just saying if it's an answer, then use the parent ID to specify the parent for that document, and then get the type of the document, because that's going to be the type it's represented as within the index, which is going to have questions and answers, and then just pass it the document here as well. Still with me so far? Yep, cool, okay. So here is us defining our index with all of the mappings. We're going to skip that for the moment because there's a lot of information there. Let's just move this to the side. Here is our bulk request though. So the bulk requests are they're line delimited JSON, so it's basically new line delimited, and the layout of them is essentially the bulk operation that you want to perform, and then if there's a document associated with that bulk operation, it will be on the next line. So we can see here there's a create, and then all of this is on the next line. There's another create operation here for the second question, and then here for the answer, we have another create operation where we specified the parent to be 1, which is this question here. And then what we see we get back from the bulk API is we get back a collection of items where each item in there represents each of the items that was in our bulk API call. So we can see each one of these succeeded, 201, 201, 201. So you can have in a bulk operation some operations may fail. That doesn't mean the entire thing fails. It just means that those individual operations have failed and you might want to retry them. So that's the bulk API. And you would use that essentially to get all of your documents into Elasticsearch if you are running purely with the .NET client. We have some helpers as well for being able to set up an iObservable to say, here's what I want you to do. Here's a lazy enumerated collection of documents I want you to index. Just go and do that thing, and then just tell me each time you're grabbing a bunch of those documents and indexing them, and just tell me when you've completed. So some helpers there that we've built on top to be able to do that kind of stuff. You can also update documents, of course. You know, it wouldn't be CRUD if you couldn't update, it'd be CRUD. So yeah, we can just index a question here, and then we can actually just send in an anonymous type with the properties that we want to update, and then we can call the update API here. So we want to update a question type, but we're only going to give you an anonymous type for the properties that we want to update. And then we can go and grab the document at the very end as well. So if we're to run this, it's all a regular affair. It's all pretty casual stuff, pretty usual stuff. But we can see at the end here, our document has been updated. Okay, let's get on to some fun stuff. Okay, so on to mappings. So that was basically indexing, bulk updating, bulk indexing and updating. So let's get on to some fun stuff instead. This is one of the things that trips many, many people up. So when you're dealing with Elasticsearch, it has this nature of being able to infer a schema from the first document it sees. But for search use cases, that's actually probably not what you want. 99, in fact, I'd say probably all of the time, you don't want that. Because the way in which the data is indexed is going to determine how you can search it. And you know usually, or you have a rough idea how you want to search it. So you want to be able to, you want to index data in a particular way that satisfies your search needs. And this is where mapping comes in. So at the point of creating an index, you can apply a mapping to an index, or if the index is already created but hasn't seen any documents yet, you can give it a mapping for a document. So in this particular case, as I said earlier, we can actually, within the client, instead of Elasticsearch saying, okay, this looks like a string, I'll map it as this particular thing, this looks like a date, I'll map it as this particular thing, we can actually, from the client side, based on the structure of your POCO, say this thing should be this and this thing should be that, and explicitly tell Elasticsearch that that is the case. And this is what this auto mapping function does here. So running auto map on this question type here is going to do some certain things. So for example, it takes this title field here and it's going to map it as a text data type. Now a text data type is the one that you use for performing full text search that undergoes analysis, which I'll talk about in a bit. But it also maps this title type as a keyword data type. Now a keyword data type in Elasticsearch is the one that you use when you want to index that piece of data verbatim, exactly as it exists in the document. And that's really, really useful for aggregations. So say, for example, in the case of Stack Overflow, you have questions that have a collection of tags on them, and then you want to aggregate on the tags to say, okay, how many questions are there with C#? What are the top 5 tags in Elasticsearch? You would probably index the tags as a keyword data type so that you can then aggregate on them. And we can just go down here and we can see the other choices that it's made here. So we can see actually for all of the string properties that we have, the client has sent through a mapping that maps it as a text data type, but also maps it as a keyword data type. This mapping only exists in Elasticsearch. It obviously doesn't exist on the POCO. The POCO only has the one property, but Elasticsearch has a notion of it being mapped as a text data type and also as a keyword data type, which means that we can query on it in those 2 ways as well.
What's the difference again?
So text data type is the one you'd use for full text search, and keyword data type is one that you would typically use for 2 things, for aggregations and for sorting, where you want to sort on the exact value as it exists. Because what happens is if you run aggregations on a text data type field, on a full text mapping essentially, or if you run sorting on there, you're actually going to be sorting on the results of the analysis on the text. So it could actually end up being split into multiple tokens and you're running analytics on multiple tokens rather than the individual, string, essentially. All that will become clear as mud in a bit. So that's kind of the auto mapping that you have in the client. There's actually a couple of other ways that you can map as well, and usually people tend to use these things in conjunction. There's a concept of attribute mapping. So here we can say our user type should be a developer type within Elasticsearch, and the ID property for a user should actually be the display name. So Nest has a convention, and this is actually exclusive to the Nest client only, whereby if your POCO has an ID property on it, that ID property will be used as the ID for the document. So you can send through a POCO without any ID property, and Elasticsearch will auto-generate an ID for it. But if you have an ID field, case insensitive, then Nest client will use that as the ID for the document, which is really useful, right? So we have attributes here for all of the different types of data types that you can map things as. So I can say here for website URL, I want you to map you as a text data type and use the white space analyzer. And I'll talk about analyzers in a second. So here in this particular example for this user, we've auto mapped. So we've done what we did before, which is basically say, hey, Nest, figure out what the mappings should be for each of the properties on this POCO. But then using properties here, we can override any of those inferred mappings as well. So we can say, actually, for this age field, I want you to use a byte rather than an integer, which is how it's represented on the POCO. And for this badge type, which is actually a collection of badges, where each badge looks like this, I want you to map it as a nested type. Now, there are two different ways in which you can map collections on POCOs. If you do nothing, it will be mapped as what's called an object type. And an object type essentially is you can query on individual fields within an individual document in the collection, but that's usually not that useful. What you usually tend to want to do is maybe do cross-querying across the individual fields within an individual item in the collection. Because what happens behind the scenes if you use an object type is that, in fact, all of the fields from all of the individual items in the collection get flattened out into just the set of fields that exist in an individual document. So you lose the association between where the value came from and which particular instance, which means that you then lose the cross-association between any of the individual property values on an individual document in that collection. So nested types will allow you to overcome that limitation, and you can then query on individual items in that collection. We can also map using a visitor pattern as well. So we can pass here, for example, this keyword visitor, so that whilst we're mapping this user, we can say, I want you to auto map, so infer the mappings here. But again, if you come across a property type of string, then I want you to map it as a keyword property only. So we can pass in a visitor to say how we want the mappings to go through. So we can see the result of that here is that all of our string fields are mapped as keyword types. That's usually very useful for log analytics use cases where you typically just want the values represented as keywords. You tend to not want to search on them in the same way in which you want to usually search on bodies of text. So cool, that was a lot of talking. So we'll just jump back in here to into the slides. So there's a whole bunch of search queries that you have available. Full text search queries, which we saw briefly there. The match phrase is a full text search query. You also have term level queries, which are very different to how full text search queries work. So full text search queries undergo this process of analysis at index time and also at query time, which I'll talk about in a sec. Term level queries actually undergo no analysis on the query. So what you send into the query has to basically match exactly what is in the index. There's span level queries, which is finding a word here within the text and say another word in the text and what the distance is between them. There's a whole family of span queries to do that kind of intra-text search. Compound queries, so it's great I can do full text, it's great I can do term level. How about being able to combine all of those into a compound query? This is where these come in. So typically Boolean queries are the ones where you can combine full text with term level with other full text, and that's how you typically build up a search strategy. There's other compound queries there as well. Things like more like this, which I have an example of. GeoQueries, kind of name says it all really, being able to find things that exist within a polygon, a GeoJSON polygon, being able to find a distance between this thing and that thing, or show me stuff within a particular radius. And then obviously you can still combine it with all of these. Joining queries, so I briefly talked about nested types there, so that internally is represented as a join between the root document and the nested documents there. But we also have the ability to perform parent-child, as I showed you with the questions and answers, and specialized queries, which are just a different beast altogether. So we will touch on that very, very shortly. But you essentially have a multitude of tools available to you. Unlike, for example, in SQL Server, everything you can do in SQL Server, you can do in Elasticsearch. The typical queries you're used to running would typically fall into what would be term level queries in here. So finding this exact thing, or finding a prefix, or finding a wildcard, or finding a regex, using a regex, you can perform all of those in Elasticsearch. So here's a very quick example. So we're just going to create an index. We're going to stick 2 documents in there. Title, how do I use Elasticsearch with .NET, all about Kibana. I'm going to bulk index those, and then we're just going to search using a match query, which is one of those full text queries I was talking about. And we're going to search for Elasticsearch Kibana. And if we run this one, and we look at the results, we get back both documents, as we would expect. All about Kibana comes back with a score of 4. Interesting. How do I use Elasticsearch with .NET comes back with a score of 2. So we can see here actually that the All About Kibana document came back ahead of the How do I use Elasticsearch with .NET. Why might that be the case though? Because one of them contains Kibana, one of them contains Elasticsearch. You know, it matched on both of those. What's kind of affecting this scoring? Well, there's something I should clue you into here actually, which does affect the way in which scores work. And that's to do with the length of the field that we're targeting. So the field, how do I use Elasticsearch with .NET, is longer than All About Kibana, which means that finding Kibana in All About Kibana versus finding Elasticsearch in how do I use Elasticsearch with .NET, it's probably, you know, the term frequencies are the same for both of them, but this one contains more words. This one contains less words, All About Kibana. So therefore, if we find it in there, we should give it a higher score. And that's actually called norms. So that's normalization factor within Elasticsearch. We can disable that if we want to, which I'm going to do now. And I'm just using a visitor to do it. So anytime you see a text property, just disable the norms, just set norms to false in there. And if we run that one again, and we have a look at the results, we can see here now that the scores for each of them, they're different than what they were before, but we can see that the scores here for the 2 documents are exactly the same. So we disabled norms, so it's no longer taking the length of the field into account, which is typically, I've found typically that's usually what you want to do. The intention there is to favor things such as titles over bodies of text. That's the intention. So if you're targeting multiple fields, give more weight to the shorter fields than the longer ones, because the chance of finding the probability of that token being more relevant in the short field, you know, is higher than it existing in a bigger body of text. That's the intention anyway. So let's go on to the term level query here. So this is a not analyzed query. And if we run this one, so we're just indexing the same documents as before, except I'm not showing it now. I'm just, believe me, it's happening. And we're just running this term level query. We get no results back. Why might that be the case? Well, it's actually because the title field that we're targeting is being analyzed when it's being indexed. So it's a text data type, and it's being analyzed. And what we're doing here is we're sending through a case-sensitive Elasticsearch here, which isn't matching the way in which the original text from the document when we indexed has been analyzed. So if we look at the next one, if we send it through lowercase, hey, we got a result. So we got, how do I use Elasticsearch with .NET? So we can, what's kind of going on here? So as I said before, term level queries, the actual input to the query undergoes no analysis. So whatever you send to a term level query, it's going to look exactly for that in the inverted index when it's querying Elasticsearch. And because our original data in our original document underwent analysis when we indexed it, it should be clear, hopefully, that the tokens that have been produced as a result of that analysis are probably not, they don't contain any casing, because we saw a match for lowercase Elasticsearch, but we didn't see a match for uppercase Elasticsearch. If we were to target the keyword field here of the title, because we've indexed it as both text data type and keyword data type, so we can use this handy suffix here. So we can still use a lambda expression to say target the title field, but I want you to look at the keyword field of the title. And we send through exactly what the title was, we should see a result there, which we do there. So that's term level, that's kind of full text queries, term level queries. Here's a geo query. So say, for example, I'm looking for where in this list of suburbs, which are Australian suburbs, where does this point exist? In which suburb does this point exist? So this is just looking at all of the Australian suburbs, which I think there are 8,600 of, and just tell me where that geo coordinate is. So it comes back, and it's where I live, which is Manly. Hooray. And we can then also say, given a geoshape that is already indexed, show me other geoshapes that are indexed that intersect with that geoshape that is indexed. So we can use this geo-index shape here, and we can say, given this suburb with this ID, which is the one we saw in the previous query, Manly, basically show me the surrounding suburbs, show me the suburbs that lie next to that suburb. And then we also then want to exclude Manly itself from the results there. So if we were to run that query, Queenscliff, North Manly, Manly Vale, Fairlight, those are the surrounding suburbs. So I can show you that's the case. Here's Manly here, here's Fairlight, here's Queenscliff, here's Manly Vale. So that's geo queries. More like this. So this falls into that specialized field that I was talking about. So given a document or given just a piece of text, show me other documents that exist within Elasticsearch which are like this one. So there's quite a few heuristics and algorithms that determine that likeness. Most of them are based on text-based likeness. But if we were to say, look for Stack Overflow questions that have the text reduce shards in Elasticsearch in the title, and we want at least one of these terms to be in the title, then we can get the results back from those. And if we just zoom in, we can see here that, oh, we're gonna be able to move. Yep, we are. So we can see here the titles here, reducing number of shards, full cluster restart. We can see these are all related to Elasticsearch by the tags. We can also see that they're all roughly related to shards or to sharding in some way. So that was a more like this query. And we'll skip that one in the essence of time. So function score query here is another one that's very, very useful. So we can do something such as say, show me documents which are like this other one, but maybe we want to take features of the particular documents that would match. We want to take features of those and use them to influence the score of that particular document. So we can say here, so it's rather nested. You can see that nest itself gets rather nested in Lambda expressions, but hopefully this, if you lay it out in this particular way, it tends to mimic exactly what the JSON structure looks like for a query. So here we're just saying, so source includes only bring back the title, score, and creation date for each particular document. And in our query then, we want to perform a function score query. So the query that we want to run is the more like this query that we just ran, which is reduced number of shards in Elasticsearch. But then we want to apply some functions to the results there as they're coming back. And those are here in this particular example, we want to say any question that's happened in the last 182 days, the last 6 months, and anything that's within the last 3 years, we want to decay the score for them at a gradual, so that would be a linear decay. So anything that is after 6 months up to 3 years, we want to reduce the score for it. So if it's older, we want to give it a lower score. So the premise here is that newer questions in Stack Overflow are probably more relevant than older questions in Stack Overflow. So we can influence the score there by taking the creation date of the question. This field value factor is another function that's going to run, which is going to say take the score of that question, and so long as it's greater than 0, we want to apply a 1.5 factor to it. So take the score and take the square root here actually, and apply a factor of 1.5. So higher scoring questions we also want to be more relevant. So these two functions are going to also be running in combination with it matching more like this. So we're going to take the results of all of those things together, and here we're going to multiply the score of all of them to give a final score to a particular document. Does that make sense? So if we have a look at this one back here, sorry, let's jump to this one here, which I think shows us some details. So let me just zoom in here. We can see that the results just from running a more like this query, we can see there's a whole bunch of questions here that actually have not very high scores on them. So they might be poorly worded questions, they might be very, very specific questions rather than general questions about Elasticsearch. So we want to basically get some more relevant questions in the results here. So if we were to run our function score query and check out the results of this one, we can see here now how our functions have affected the results here. So we have some higher scoring questions coming back as being more relevant, and there's an influence of more recent there. So these particular ones here, they're probably more relevant for the text-based, and we can. There's another API to understand the breakdown of a particular score, which we could use here to understand why this one here that's 4 years old appears higher than this one. We can see, just eyeballing this, probably because this one has a higher score and the title is probably more like the title that we asked for. So that's function score queries. So that's a specialized type of query. Very, very useful. So compound queries. Here's a Boolean query. So we want to look for documents that match with Kibana in the title or match with Elasticsearch in the title. If they match with Elasticsearch, then give them a slightly higher boosting. So boost their score by 2 here. And then we also want to filter. So we only want to look for questions here that do have a score greater than 0. So any negative score questions we're not interested in. So we can combine all of those things in. So Kibana or Elasticsearch in the title, and it has to have a score greater than 0. That's essentially a Boolean query. That's how we combine a collection of queries into one. And we can combine them in and, ors, not, and filter configurations. Filters here, queries that run within the filter section here do not undergo a scoring phase. So typically with unstructured search, where you might do, for example, range queries, or does it match this thing exactly, you typically don't have scores for those things. They're a predicate, they either match or they don't. You typically want to put those into the filter part of a Boolean clause if you're combining them with other queries. Nest has a very, very nice shorthand for being able to specify Boolean queries by overloading the operators on queries. So we can OR these two queries together. So M goes to, yeah, so match query here, or this match query, and plus. So plus unary operator here is used to specify a filter query. This is exactly the same query as we saw before. And this one here, oh yeah, it just shows off covariant search results. So we can ask to search on the posts, We're interested in questions and answers, and we can perform an async await, search for anything that matches async await in the body, and we can see with the results here that we get back questions and answers in that results collection. Cool, okay, so that was a very, very whirlwind tour of search queries. I'm going to skip through this very, very quickly because I can see it's very hot in here. I talked basically around text data types undergoing analysis. What was I blathering on about? Essentially, they undergo analysis using an analyzer. So what does an analyzer do? It takes in a stream of characters. It runs them through 0 or more character filters. It then runs that through a tokenizer, which tokenizes that text into individual terms. And then it can run those individual tokens through 0 or more token filters. And at the end of it, you get a collection of tokens which are indexed into the inverted index. And when you perform a search on a text data type field, you're going to be hitting the inverted index, and your query will also undergo analysis, and the tokens produced from that will be compared to the tokens produced at index time. So the standard analyzer is the one by default. If you don't specify any particular analyzer, it's going to use the standard one, which doesn't have any character filters. It has a tokenizer, which is called the standard tokenizer, funnily enough, which undergoes Unicode text segmentation algorithm, which has very different, has a complex set of heuristics for how it determines where to split words. So it will split on white space. It may split on a dot if it's at the end of a word, but not if the dot exists in the middle, and various other heuristics. So it generally does a pretty smart job for Western languages. For Eastern languages, it's not that useful because they have very, very different rules around how they form words, and usually they compound things together. So standard analyzer is usually no good. You want to use a specialized analyzer for that stuff. And then it goes through token filters. Standard token filter doesn't do anything. Lowercase token filter, so standard token filter is a placeholder for future things. Lowercase token filter, lower cases. So we saw there Elasticsearch when it was capitalized, didn't match the standard analyzer because the standard analyzer lower cases things. And then the stop token filter can remove stop words. So it can take out those common words like the, is, and, which are of no use for search generally, and you want to strip those out. And we can also build analyzers to perform things such as stemming, lemmatization, in order to take, for example, running, runner, runs, and stem those down to the root form of the word. That's essentially what we can do with analysis. We have full control over how we decide that that data is analyzed. To give you a quick example, if we were to say F# is clearly the superior language, if we were to run that through the standard analyzer, first of all, the tokenizer is going to split into these tokens. So we can see that the hash, the pound, has disappeared. So as our stars around the, it's lost some emphasis. We can see the standard token filter, as I said, is a placeholder. It isn't doing anything here to the tokens. But the lowercase token filter is obviously going to lowercase everything. And then the stop word token filter in the standard analyzer default actually doesn't remove stop words. You can derive, yeah, it may trick you, but you can derive an analyzer from the standard analyzer and say, hey, remove English stop words, please. I think it should remove them by default personally, but that's a discussion to be had with the team. And then all of those tokens go into the inverted index. So for that particular field, which is title, we can see the terms that have the result of analysis and then the document IDs from which they came. And just to jump very, very quickly, because I realize time is flying by, if we were to just skip over all of these and just jump into analysis, this is essentially what how you would define an analyzer. So at the point of creating this index here, we can specify the number of shards that it should have. So for demonstration purposes, I only need one, no replicas. And then under analysis, I can specify character filters, analyzers, and token filters. So let's just take a very, very quick walk through here. Character filters are going to strip individual characters from the token stream. So we set one up here and call it programming language. It's just going to call this function, and all that function is going to do is it's just going to take anything that starts with C sharp, F sharp, M sharp, J sharp, S sharp, A sharp, I've never heard of that, K sharp, T sharp. It's just going to take that and change the hash to sharp so that we don't lose it when we send it through the tokenizer, because we want people to be able to search with C sharp with the hash, but still be able to find C sharp results and not C results, as they would if we just let it run through the standard tokenizer. Then what we're going to do is set up a token filter here. So we're going to call it our better synonym token filter. So anytime it sees superior, better, or greater, it's also going to introduce the synonym for that one as well. So these are all bidirectional synonyms. So superior, better, greater, any of those will also have the synonym for that. And then we're just going to define two analyzers here, two custom analyzers that use those pieces. One we've called HTML, which uses a HTML strip, a character filter, which is an inbuilt one in Elasticsearch, which just takes out all of the tags. Because usually if you're searching on a field that has, HTML tags in it, you don't want those in there. You want to strip all of those out. Then we're also going to use our programming language character filter. We're just going to use the standard tokenizer because it does a pretty good job with that Unicode text segmentation. And then we're going to use our token filter. So standard, lowercase, use the stop one, and then we're going to use our better synonym. And then this one's really just the same as this one here, except it doesn't strip the HTML tags. And there's a reason why we might want to do that. Here on our question type, when we're mapping it, for the body field, we're going to say use the HTML one, so strip HTML tags when we're indexing, but when we're searching, use this analyzer instead. So when you're searching on the site, you're not going to put in HTML tags as you search. So there's no need to do that HTML tag stripping. So we can use this other analyzer that doesn't need to do that. So if we just run this very quickly, so we can see the mapping that was generated from my function. Yeah, so we can see that one generated from the function, and this is the mapping for the question type. And yeah, it succeeded. So if we go to the next slide here, and then we just use the analyze API, and just see what F sharp is clearly the superior language comes out with the standard analyzer, and then we see what comes out with our expand analyzer that we just created, and just compare the tokens that we get out for both of those. So we can see the standard analyzer F is clearly the superior language, and we can see with our expand one, which has our synonym token filter in there, we also have the better, greater synonyms in there as well. So someone looking for F sharp is the better language is probably going to come across our question if it had the superior language in it. I'm going to fly through aggregations because they're kind of cool. Yep, so that was all search. It's very, very useful for lots of things, but you can also aggregate your data. So metrics, being able to aggregate individual metrics, sums, averages, mins, max, that kind of thing. So individual values, getting those out of there. Buckets are an interesting one. So just basically dropping things into buckets based on, say, date range. So if it's in the last week, it goes in this bucket. If it's in the week before, it goes in that bucket. And with bucket aggregations, we can also sub-aggregate as well. So we can put things in a bucket here and then sub-aggregate those buckets, and we can go n levels deep in buckets. Geo, so we can do geo aggregations, so stuff that falls within 5 meters, 10 meters, 15 meters. We can do that kind of stuff. We can build where it falls on a geohash grid. We can also perform geocentroid aggregations, which are really an extension of geohash ones. So if things fall within a grid, and that grid is a representation of what the world looks like, then say things happening in this particular part of a grid, we might want to center those to the average of an overall area. So just move those particular points with a geocentroid. It's much easier to show with a demonstration, but I probably don't have time for that. And matrix aggregations, which is essentially build a matrix from a particular field within a document and give you statistics about that particular field. Making sense of data, have a look in Kibana. Just have a look at that very quickly. So I indexed all of the data in the .NET Core telemetry. So anyone else have a look at that data? No, so they released it basically on the tooling, what was happening there, and they've released these in tabs, separated value files. So I just wrote a very simple logstash configuration, happy to share that afterwards, to index that data into Elasticsearch and then build this visualization here. So if this was, this is static data here, so this is never going to change. But you can build these dashboards on data and have these dashboards update real time as that data is coming in. So we've just built some pretty charts. All of these charts are built into Kibana, and we can click on these. And when we click on a particular area, all the other charts are going to refresh based on our particular choice there. That was really a very, very brief overview, and I realize I've gone way, way over time, as typically happens. But yeah, hopefully that's given you a flavor of the kind of searches you can do, and the kind of things you can also aggregate on. I'm happy to chat for however long you want to spend afterwards, going through particular issues you might be facing. Just wanted to call out this new search app. So we have a repository where we do a walkthrough of building out a .NET Core web application that uses Elasticsearch to perform search on NuGet packages. Because we all know the NuGet search is good, right? And in fact, we can go and hit this site if we want to go and just go to newsearch.ch. It should be up. It's on Azure, so you might have to give it a nudge. I'm on Wi-Fi. Hey, there we go. And we can go and search for things here. So all of the data here is entirely powered by Elasticsearch. So if we're going to search for Elasticsearch, yeah, you can have a play with that, and we can page through data here, and we can bring back 50 packages. And we can click on each individual one of these, and we can see the query score here. We have some facets or aggregations down the side here as well. So Microsoft seem to be doing pretty well generally for packages on there, because we probably have a few different versions for .NET Core, DNX, and various other strands. So yeah, please go check that out and have a look. It's a very comprehensive walkthrough there of dealing with different kinds of queries, function score queries, match queries, query string queries, and it walks through some of the pros, cons, the trades off, the pitfalls, that kind of stuff. So I highly recommend on that particular branch as well. Go and have a look at that. Some other resources, if you're very, very interested, we have the reference online. So obviously a reference for all of the versions we've completed, but also next to the reference, we also have the definitive guide online. So you can buy it as a book currently, but the book is based on Elasticsearch 1.3, and we're on Elasticsearch 5.6.3 right now, about to release Elasticsearch 6. So the definitive guide online is currently at version, along with Elasticsearch 2, it's in the process of being updated for 6 because there's a lot of changes. But yeah, have a read of that. It's a really great book to get started with stuff. .NET clients there, go and have a look, file some issues, open PRs. Yay, we love PRs. Just have a play with it. And yeah, file any issues there that you come across as well. Very open to talking about, you know, problems or improvements that can be made to the client. And then the documentation for the client exists on the Elastic site as well. And that's fairly comprehensive. It's generated entirely from our tests, so it doesn't drift. We use Roslyn to walk the AST and generate the documentation from that. Finally, one more thing. We do have our user conference, our global user conference in San Francisco, February 27th to March the 1st. I am not trying to sell this to you. Well, actually I am, because it's awesome. But I wanted to call out the fact that there's a call for papers here, 31st of October. So if you have some interesting use cases already, please submit a paper for this. Elasticsearch will obviously, you know, help you get there and accommodation. So, you know, if you have some interesting use cases, please do come and share them with us. We've had some really cool people talk from, you know, Uber, Tinder, NASA, United States Air Force. Bunch of different people have talked about various different things, and it's usually really interesting stuff that I would never think to use the stack for. So yeah, thank you very much. Hopefully that was useful for you. Thank you.